All right, my name is Emilio Botero, and I'm one of the lead developers of Swab, and I'm going to go through a UAV tutorial on how to build up a tail sitter. So for this tutorial, you'll need a Linux, Mac, or Windows machine with Python 3.6 or greater, Swab 2.5.1 or greater, and then all these packages that are required by Swab. Optionally, you can have OpenBSP, and after this, a link to this video will be uploaded to Swab's website, swab.stanford.edu, with the files to follow along. The vehicle that we're going to model today is the Transition Robotics Quad Shot, and this is a 4-rotor vehicle, and just with a simple wing. And what we're going to do with this is just model it. And the purpose of this tutorial is actually to show how to do a complex mission. So it's a very simple vehicle, but it has a very complex mission profile. So we'll model the vehicle's profile, including transitions, both from hover to forward flight and back. And yeah, let's dive in. So what we're going to do for this is we're going to build up how you would do this from scratch. So everything in this tutorial is based on data that's available on either now or prior on Transition Robotics website. So none of this material is anything that's proprietary. It's just openly available, or some of the numbers may have been judgment numbers based on just educated guesses. So for example, the location of the motors I used just based on the size of the wing and just kind of eyeballed it there, but that doesn't make a huge difference here. So we'll start off. Usually I like to name my files. So this will be QS tutorial. And we're going to work through this kind of line by line. And then I'm going to put my name here just so everyone knows I wrote this. So the first set of thing we're going to do is we need to have a set of imports. And there's going to be, as I go through this tutorial, I'm going to have on the left, I'm going to do this live, type all these out and explain what everything means. And on the right, it will be the actual code that works so that we can kind of verify as we go through. So the first thing I'm going to import is I'm going to import Swab, of course, because we're going to run Swab. And now from Swab, we're also going to import units. So the units package allows us to specify different units that are going to be used. So for some things, I may be using inches or feet, or maybe some SI units. And so it's nice to declare which ones we're actually going to be using. Now for the next one, we're going to import PyLab. That's a plotting tool. Some people may have matplotlib, and it'll be slightly different. So you can do import matplotlib .pylab as PLT. Next one is copy. I'll show you where copy is used. Copy is used, we're going to use deep copy because we'll have 4 different rotors and they're all pretty much identical. So we'll copy the rotors. And now the next one is plots. So I'm going to copy this directly over. This is just a regular plotting routine, and we'll put that there. The next one is propeller design. I don't actually have data on the propeller. So I'm going to make some engineering judgments, and we're going to actually design a propeller that will meet this mission requirements. The next is the battery sizing. Now I could have actually just looked up online what the battery specs are, but again, this will demonstrate how you can size a battery pack, make some assumptions and size it out. And similarly, for the motors, I actually didn't know what the motors are, so I did a sizing routine here. And I will caution, if people are interested in this motor sizing routine does have the assumption that it is for drones. So I would not use this for anything eVTOL related. All right, we're going to work a little bit top to bottom, but there'll be a couple spots where I'll go all the way down to the bottom. This is one of the next things. I'll put this main here so I know where the main is. I like having that. So the main function here is going to have what order I'm going to actually do the sorts of setups and analyses that I need. And to call main, I actually need to run, because this is Python, I need to run the whole script, and needs to actually be able to interpret the entire script from top to bottom, and then I can run main. So what I'm going to need to do is go all the way to the bottom here, and I have this if statement here, if name equal main. So this means it's going to be executed from either a Python shell or this debugger here. And I'm going to copy this, and this is going to live all the way at the bottom. So this is a necessary line, and that will call main. So the first thing main will do is going to do this thing called full setup. Actually, I'm going to need to def main. So main has no arguments coming in, and it's going to set up a set of configs and analyses. Now the quad shot does not have any different types of configs, so there's no rotors that change positions or anything like that. But it's nice to kind of build up this sort of this template in case you do have, for example, a landing configuration as opposed to a cruise configuration in your vehicle. The next is there's a configs.finalize. Because we only really have one config, it's not really going to do anything here. But the next line, these analyses.finalize, is incredibly important. That usually what this will do is it will set up all the analyses and connect them. So if you have an analysis, so for example, vortex lattice, it will run the vortex lattice in advance and build all the data that it needs. For this, we're not going to use a vortex lattice. We're actually going to use a different method, and I'll talk about what that method is later. But that also requires a little bit of pre-computation. And then next, we're going to run the mission. So we're going to set up the mission, and the mission is analyses. So the analyses are set up here, or sorry, the mission is set up in the analyses in this case. Now there's more than one way to do this, and some other tutorials will have the different hierarchy here of how you set these up, but this is just the same general flow applies. And then we'll evaluate the mission. So there's good reason why I'm putting all this first, as I want to show you the flow of the analyses I want to run for this case. So I'm gonna create a vehicle. I'm gonna specify what type of methods I'm going to use. This will then set up those methods, and then it will evaluate those using those methods through the mission, and it will actually fly the vehicle and see how it performs. And then finally, I'm actually just going to plot the mission. I'm going to see how that quad shot performed here, and I'm going to see the results. I put this plot.show after main, so these plots that are generated will then pop up on the screen, and we can take a look. All right, so the next function is full setup. So we'll make this, actually copy this one because I'm going to retype this. So do full setup here, and we'll def. For any folks that are live, if you have any questions, feel free to stop me, and I will be happy to answer questions. So now this is similar to main in that we're going to now call other functions that we're going to be putting together here. And the first one we're going to call is the vehicle setup function. What this does is actually create the vehicle, so it instantiates all the data necessary to specify the geometry. So going back to that picture we had, basically on TRI's website, they had a wiki that had all the dimensions of it. And I was able to pull off, for example, reference areas and other dimensions of the vehicle. And I use those directly to do this. So this will call that function. So we'll just copy that over, and that will create the vehicle. And now we'll do a config setup. Again, like I mentioned, we only have one config, but we're still going to do that anyways. I think it's just good practice to use configs, because oftentimes, if you start a process without assuming you're going to have different configurations, you only have one, and then later on you're like, oh, well, I want to try, a different change to this vehicle, and you only have set up all your scripts assuming there's only one vehicle ever, it does handicap you later on. You have to go back through and change things. But if you're like, oh, you know what, actually, I want to just try 2 different cases, it's really quick to change those. Next, we'll set up the analyses. So the analyses, this is where we will specify the aero model that we want to use. Now, the aero model used for this drone is very different than the aero model that we use for full-scale aircraft, for manned aircraft. It's for low rounds number, and specifically for transitioning vehicles that have that flat high angles attack. So I'll discuss that when that comes in a little more detail. The next is we're going to set up the missions. So this is takes the configs and analyses and then sets it up for all of these. So I'm just going to copy these over. And then finally, these are all of the analyses in a container. I'm trying to think. These are Yeah, these are necessary because they have all the configs. So this is just a way to bookkeep it. This is, like I said, not the only way to do this, but this is one way. And then that will return back to this main function, configs and analyses. So return configs and analyses. And as we go through what a config and what analysis is, will make a lot more sense. But now the next thing in our hierarchy, so we've done the main, and then main calls full setup, and then full setup calls vehicle setup. So let's build up the vehicle setup. And this will actually specify, and this is a lot of the meat here of what actually is quad shot. So we'll do def vehicle setup. And then we will start with a swab. The vehicle will be a swab.vehicle. So this swab.vehicle is an empty vehicle, but it has all the properties and the data structure already laid out. We're going to give the vehicle a tag that just gives it a name, and we're going to name it a tail sitter. Now, the next thing we're going to do is some high-level properties. These are, for this, we're just going to do weights. For an electric vehicle, it's really easy because the weights are basically all the same. We're assuming we're not dropping anything. We're not going to carry any payload. It's just going to be that little drone that we saw in this picture. So vehicle.mass properties. So notice here I am using ID, so it'll show me mass properties, and then I can do takeoff. And that is equal to 0.82 times my units.kilogram. So swab defaults to SI. So if you're using an SI base unit, you can actually just ignore the kilograms, but I like to specify that it is in kilograms so that if anyone reads this later, they know, hey, I'm using kilograms. So mass properties and then max takeoff. Okay, the next number that is at the higher vehicle level is the reference area. So the reference area doesn't necessarily actually have to be the area of the wing. In this case, it is, but in other analyses, you may want to choose a reference area that's just something consistent for your vehicle. You know, for example, you could always have a reference area 1, regardless of your vehicle size. So that's kind of a user's choice. This is not actually, doesn't have to be a physical number. It can be whatever you want it to be. And it is 0.1668. And then times units.meters, and then it's actually squared. I didn't put meters squared there. It actually doesn't matter because I'm using base SI units. Now, this vehicle is pretty simple. It just has a main wing. We're not going to analyze those little pods that come off because I don't have the full geometry of that. And it really won't affect much because in this tutorial, we're not doing any sort of turning flight or anything fancy there. So it really won't affect any sort of beta angles or anything there. So I'll just put this here. I like to have these little blocks so that I can see what I'm writing. So the wing, that will be a swav.components, so physical components, and then wings, and then I'll assume that it's going to be a main wing. So it's a load carrying, has ailerons, those sorts of things. Haven't specified any ailerons, but it is that of that kind. I'm gonna call it main wing. You call it whatever you want, but main wing works. And now we're going to go through and we're going to specify things. So the wing areas is the first thing. So we're going to do a sizing after. So the wetted areas will be calculated, and we're going to set that to be the vehicle.reference area. So we'll link those together. That'll give us a freebie there. Wing dots, sorry, there's an extra S there. Spans dot projected. So I'm going to do a projected span here. And this is 1.03 units.meters. Again, just found this on their website. Aspect ratio. So for some reason, my aspect ratio wasn't B squared over S. I could enter this in directly. But again, I already know it's going to be b squared over s, right? So this is my projected span squared divided by the reference area. So again, basic relationship. And then I'll put that in here. So quick eyeball of the vehicle, had the sweeps at about 5 degrees. There's not that much sweep. It's pretty straight. Sweeps record, and it's 5 times units dot degrees. Now, one of the base units in SWAB is radians. So if you put 5 in there, it would be 5 radians, which would be very different result than 5 degrees. This is another assumption I had to make. I don't know what the airfoil is. So I said it's probably something that's relatively symmetric. And I said maybe it's like a NACA 0012. So that's an explicit assumption I made right off the bat. Now the wing dot taper. So this is the taper ratio. I believe just by looking at the pictures, it's about 1. If you had more detailed knowledge, you could actually say what that is. But for now, we'll just do 1. Now that dynamic pressure ratio is the next thing. This is used for cases where you're going to do stability analysis. So we actually don't need this for what we're doing. So I'm actually just going to not do that. So this is for a stability analysis. We're not going to run a stability analysis. And I'll go over that later. That's mostly used in the case where you're doing a buildup of wings, where you have a wing influencing another wing, and you're not going to use the VLM. You're going to use handbook methods. So we're not going to do that. So the next one is wing dot chords dot mean aerodynamic, and that is 0.162. The next one is, I'm sorry, folks, this is just a lot of data to enter. So there's no twists because, so if you're familiar with a quad shot, it actually can fly upside down and right side up. So there's no twist there. I've actually flown this vehicle by hand as an RC plane, and it flies just as normal upside down as it is right side up. So there's definitely no twist. There's no washout. There's nothing like that. So I know that there's nothing there. 0.0. And now these other flags just are useful in SWAV. So wing dot high lift, that is going to be false. So this is not something with flaps. So when it's doing a calculation, maybe to calculate CL max, it's saying, hey, I don't have flaps. I'm not trying to do any sort of thing fancy. So it's just using a clean wing. And now wing dot vertical, this is just indicating that it's not a vertical tail. And so this is a rotation of the wing. So rather than being in the XY plane, it would be in the XZ plane, but it's not a vertical. So that's a default of a main wing, but I usually like to include it because you can just kind of be sure that, like, hey, I didn't make a mistake. It didn't actually set it up to be something different. Now it's symmetric. So that means that it is symmetric about the XZ axis in the vehicle. So there's a wing on the left side and the wing on the right side. That's what that means. Actually, I didn't do a sizing here, but that'll be fine because the way the back drag built up. Okay. So the next thing is we've built up the wing and we want to add it to the vehicle. So append component, and we're going to append this wing. You're probably also wondering, what sort of options do I need to add here? So probably some of these are unnecessary because they're already defaulted. So like I mentioned here, the vertical is defaulted. I believe high lift is false. Some of these things are 0. Well, that already be defaulted to 0. And I can actually show you what those defaults are. So if I click on this main wing, I can look at the defaults and you're like, oh, there's no defaults here. But those inherit from wing. And so wing has a set of defaults. And these are all the possible parameters here. Now, it can be hard to know which ones I actually need. But I happen to know the analyses that are being called and know what the minimum set is. Or some things are just going to be defaulted to 0. So for example, the location. So I didn't really put an origin in here. I can put the origin, and maybe we should do that. It'll be slightly back in the X direction. So I'll go back here and say, hey, because actually, if we look back at that picture, the origin is the wing's slightly back from the origin, but it's close. So it's going to be about 10 centimeters back, maybe, maybe not even that much, maybe 5 back from the front, which would be where the propellers are. So it'll be back in the X direction. That's only really useful for plotting, but won't actually affect the results. So again, this has the list of all the possible things, and you'll see some of these are here. Anything that we didn't actually select are just things that would be defaulted anyways, and we don't really have to deal with. So for example, the leading edge sweep or the half chord sweep, really don't need that for right now, and maybe those be calculated later if we need them. All right, so that's the wing component. And in other tutorials, we'll go over more detail on how to make those wing components in a little more detail and what they do, because that's a fairly simple wing. The fun part here is actually designing out the propulsors. So for this, we're going to do, it's going to be a drone. So it's going to be an electric drone, and this is going to use a battery propeller network. So this is used a lot for drones, but also used for eVTOLs. So this is something that's applicable for a lot of different types of vehicles that are up and coming. So whether this is a small vehicle or a large vehicle, all of this that I'm doing right here is still totally applicable. What changes are the analyses and the mission. All right, so I'm going to start a network, and that network is going to be the SWAV components. So then I'm going to add an energy network. And now you're probably wondering, why don't I call it a propulsor? And in SWAV, we do something called networks. The thinking here was that just adding a propulsor like a jet engine or these battery things, and then you have fuel cells, and we realized that it's not just a simple, what ends up being a network for the future aircraft. What ends up being a propulsor for future aircraft ends up being a network. It's a collection of components that all operate together. So hence we decided, like, hey, the network is the obvious naming solution here. So you do need to set for this network specifically the number of propeller engines. Now it could be called motors. I don't know why we chose engines, but there's going to be 4 engines here. You can see what the defaults are here. And there's a whole list here. Some of these are not, defaults are not like true, false, or numbers, but actually components themselves. So propeller engines here as opposed to lift rotors. So we're going to assume that these are propellers because even though it hovers, it's really more of a propeller. It's aligned with the wing. So let's go. That's my live one. And now we're going to set the voltage. So the network needs to know how, what the max voltage really is. And in this case, it's going to be 12.3 volts. So it's a 3-cell LiPo that runs with it. It's going to have identical propellers. So this is a kind of a cheat you can put here. So realistically, you would have different rotations here on each propeller. But for the analyses, because we're not doing anything turning flight, we're not using an engine out, the torque should cancel. So we're going to do identical propellers. You can make that false. And what that will do is it will run each propeller independently rather than just summing up the effects of all 4 together with the thrust vectors. So this is a computational shortcut that is definitely optional, but for this vehicle, it makes a lot of sense to use. The next thing is, so this is the high level, parameters of your battery propeller, and now we're going to start adding components. The first thing we're going to add is the electronic speed control. There's really no order here that's necessary. You could do any order you want. So we're going to say we're going to have an electronic speed control, and we're really just going to be agnostic to any sort of brand or any sort of specifications because it really doesn't change too much. Really, the speed controller is really just an efficiency loss at this level of computation. So we'll say it's 95%. There's a reference here from a book that said, hey, for drones, they're about 0.95%. If you have a manufacturer that can tell you what your efficiency is, or you can specify some sort of curve, you could change this, but for this assumption, we're going to leave it there, and we're going to attach that ESC to the network. So that one's pretty simple. The next thing, now we're going to get to the fun stuff. We're actually going to design the propellers. So the propeller is a swab component. It's a converter. So the in this energy folder here, there's distributors, there's converters, there's storages, there's a whole level, and there's processes. There's a whole way of classifying things. So propeller converts rotational energy into thrust energy, basically. So it's a conversion of one form of energy to another. So that is why it's called a converter. A distributor is something that really just distributes power. This doesn't really change the form. It's still electrical energy, but the propeller changes your motor's power into air power, whatever you want to, fluid power. So I'm going to set the number of blades. I know it's a 2-bladed prop. It can be whatever. It can be an integer or a float. I'm going to, this was an assumption I made. I don't know the properties of this blade. If I, for example, had measurements of the blade, if you could go to the UI/UC database, you could actually figure out a blade that was similar. And I could actually take that data, enter it in SWAB. SWAB will accept, for example, UI/UC data. But for this, we're going to actually just size one out, which is what we often do. So at 15 meters per second, we're gonna fly the vehicle, and it's going to be at 7,500 times units to RPM. And we're going to set the tip radius. So this is an 8-inch propeller. So the radius is inch. It could be inches, I guess. Hub radius. These are fairly standard size if you flew an RC, but about a 1/4 inch. These are small little propellers. Now, the next 3 things are design criteria that I'm going to use for my design script. So these are dimensions that I've estimated, or properties I've estimated. Now the next are things that I need for the design script. So the design CL of the airfoil, I'm going to make that about 0.7. I just happen to know that that's a really nice design CL because for SWAB's design script, what it does is it looks at your airfoil, and it will run that airfoil or try to run the airfoil at that CL distributed across the span of the blade. So the airfoil that I'm going to use is a low Reynolds number airfoil, and I just happen to know that's where the L over D max is. So that'll be like kind of a nice sweet spot. Design altitude could be 0. It doesn't really matter. And then the design power is actually something I do know because I know how the motors are rated. And I think I backed this off a little bit for this design condition, but I can kind of estimate ballpark what this should be. Okay, next, as I already imported my propeller design earlier, I'm going to pass this over to the propeller design tool and give it the prop. And that will return exactly, this runs the Liebeck and Adkins routine that will actually create the twist distribution, chord distribution, as well as a whole host of different sectional information about the vehicle, the propeller. Let's go back to here. So that's one propeller, but we actually have 4 propellers. So to actually attach them to the vehicle, we then need to set up all the origins. Now you could do this manually, but I just did a for loop here that just goes through, and I just, hey, I have 4 origins. So I put 4 origins. They're all at 0 in the X direction, and then they're offsets. This one's 15 centimeters out from the center line, and this one's -0.5. We can actually go back to this and kind of see if this makes sense. So this is these motors here. This is the bottom side of the vehicle, and they're about 15 centimeters, half a foot, 6 inches up from center line, and a few centimeters off center in the Z direction. So this is the bottom of the vehicle. And then similarly for the outboard ones, they're a little bit further out, but on the positive direction. So that's what these origins mean. And we'll add them here. And then we'll loop through. I have to start going a little bit faster to keep this tutorial in time. We're gonna deep copy. So the deep copy will create an identical copy of each of the rotors or propellers, and then just change the origin on each one. So they're all the same. We're gonna assume they spin the same direction, although that's not realistic. We could change each to be alternate. So you would in the real transition robotics quad shot, this one would rotate alternately from this one, but it'd be in the same orientation this one. So there's reverse propellers. But for what we're doing right now, that won't matter because the torques will cancel. Next, we'll do the motors. This will be another question mark. So I didn't know the specifications of the motors, so we're going to size these out. And then we're going to assume a speed constant. This is something that I was able to get fairly close to, I think. So it's a 1500 RPM per volt speed constant. And then, oops. So there's this, I'm going to set the speed constant of the motor to be 1500 RPM. That's RPM per volt, but I don't really need to specify volt because that's a base unit. Next, I'll do the sizing, because again, it's only based on kV. Now, you could probably be disappointed here, and these regressions come from Gurr and Rosen here, and they regressed out a bunch of different motors, and I would use these. They're okay for basic analyses, so to get the no load current and a little bit of the mass. I wouldn't say that these are totally truth, but they'll get you in the ballpark for this sort of thing. So if you don't have any other idea. Now, there's some other things we need to specify. If there's a gear ratio, there is no gearbox here. These are brushless outrunners. There's actually don't think I need the expected current, did I? No load current. I do need the expected current. So I'm going to make an assumption that the expected current is 10 amps units dot amps. And then the propeller radius, the motor needs to know the propeller radius because that helps with convergence if the motor model. It helps calculate the torque. And that's prop.
Amelia, can I ask you a question real quick?
Sure.
It's Jonathan. You're saying you know that you need all of those in order for the analysis to work. So
yeah,
for that's all in your head, but like for someone that's new, like how do we know that we need them? Like, do we just run it and look at the errors, or is there?
That's one way. That always catches me off guard if I, for example, forgot something. Now we can go to the motor and see what it actually needs, right? And so it has all of these things. So I know here that it needs a resistance, but that's given by the electric motor sizing. The no load currents also come from the electric motor sizing. The speed constant, I entered that, propeller radius, propeller CP. Now this is this will come from the network actually. And so some of these are outputs, which is a little bit confusing here, but so the efficiency and CP will be outputs, but the gear ratio, for example, I've had to enter that here. The gearbox efficiency is 1, and the expected current is there. So the best, if you're unsure, the best place to check is in the component itself. It'll tell you, and if you're not sure, put in everything you can. And if it gives an error, usually if there's like something defaulted to 0 and there's a division by 0, later on that'll come up. But there's more than one way to do all these things. So unfortunately, there's not like one set rule. But the best way just to look at it and say, hey, it's going to call all these things, so I need to specify them one way or the other.
Okay, and you said some of those requirements at the top there were outputs, but if you give it an output and try
to
set it, is it just going to ignore it?
Yeah, so that one was the CP, and I think that the documentation there was just, this is a misnomer. This should be propeller dot inputs. So I think that's a small mistake there in that. But that's an input here actually, as well as the voltage. So yeah, that's the answer. I'm sorry that one is not clear up there. That's
No problem. Yeah, I just want to see where you're getting all this stuff from.
yeah. Hopefully that makes sense to you. Back to the live thing. So that's the motor. And then we're going to do the same thing again. We're going to set to the origins. Now, of course, propeller and motor origins, they'll pretty much be lined up for a small UAV. So I'm going to assume the same origins twice. In the interest of time, again, I'm going to speed up and start copying more things. So the next thing is the payload. In this vehicle, it's a totally clean vehicle. There's no payload. You can put like a GoPro or something on a quad shot, small things, but there's no real payload. Now the next is avionics. Avionics are like the transmitter and receiver. The quad shot has like a Lisa autopilot. That's 2 watts, maybe it's 5 watts. Not a huge difference, 10 watts. Not a huge power load, but we'll put that in there. Maybe I'll make that 5. I don't really have a good sense.
One question, Emilio.
Yeah.
Instead of starting from scratch with this script, would you use like a template script for a previous case and just make the change and update of these numbers?
Yeah, so you can definitely do that. This is like half of this script is things that I templated out, and half of this script is things that were totally new. So I would say the things that were templated or this is a pretty typical flow of analyses. Same with this full setup. Like I was saying, I don't use different configs, but it's nice to use the configs in case I do later change. But what I did start from scratch, with all of the different properties here and just kind of put the ones that I thought I needed. A couple of them I accidentally kind of just left in. I didn't have to put vertical in there, but I threw it in there anyways in the high lift. Even though those are all defaulted, but again, it's habit. I just like to put everything in there that I usually put in. So yeah, it's a mix. It's a mix of new stuff and existing things. So my hope here is that folks can download this and use this as a template and change it as need be.
I think that goes back to, I think about a week or two ago, I was asking you, and Yahya, you can correct me if I'm wrong, but I think you're asking the same question is, if you don't have the template to start on, like, how do you go about, being resourceful on your own to go and figure out what to put in, a fresh script? Yeah, and it will depend on the sorts of analyses you want to run and the sort of data that you're interested in getting. But there'll always be something that'll cross over. I found I've never had to totally start from scratch and think totally broadly. There's always been something I can steal from another script and just be like, hey, I'm just going to drop this in and change a couple numbers. I think, the payload here, like in the avionics stuff, I copy that one, the ESCs, that stuff doesn't really change except for the numbers. But a lot of other stuff will change. The vehicle geometry changes. We'll do more tutorials and you'll see in other tutorials. The geometry does change quite a bit between one sort of vehicle and the other, and that'll be quite significant. So yeah, let's keep moving on. This battery is a very simple battery. We're going to use the lithium ion. Now, there are more advanced batteries out there in SWAB that you can use, and they do require different sets of data. You can actually look at those later. I'm not going to include them in this tutorial, but maybe in a future tutorial, I will include how to use those fancier batteries because it does take a little more setup. But this is a simple lithium ion battery here. I looked online, found a battery that was similar, like a 3-cell, and made some assumptions here and just double check that those made sense with existing LiPos. So 170 grams, 175 hours per kilogram, and that gave me like a decent amount of amp hours for a battery of the size. So that's what I'm doing here, and it's 11.1. Now that says max voltage. Maybe it's a little higher, depending on your chemistry. Could be 12.3 or 11.1, whatever. So we'll leave that there. And then there's initialize from mass here. What this will do is say, hey, what's my specific energy?
what is the mass, calculate that out. I know you can do that calculation in your head. It's not a big deal. You can write it down. But this does it and adds a couple other little things here too. It also calculates specific energy, specific powers. And if you had different cells, for this tutorial, we're not doing cells, but you could also use swab. You can build up different cells and put them together into one pack. All right, so that gives you the battery. And now we're going to append the whole network. And then return the vehicle. All right. This will go through fast. We're going to talk about configs. That's the next thing in our flow here. So we created the vehicle. Now we're going to set up the configuration of the vehicle. Again, the quad shot doesn't really have different configurations. So there's just the base configuration here. Again, I think it is worth your time to put in a configuration in case you're like, you know what, let's make a giant quad shot. I think TRI actually has like a super quad shot that they didn't release, but they actually built, and you could see how those look. The super quad shot has like big motors. They're able to put things on it, things like that. So that would be a case for a config, and you can see like, hey, if I swap out the vehicles, what happens here? This analysis setup, again, this is something I'm just going to copy and paste. This is something I copy and paste every time. Basically, this just goes through the configs. So if I have multiple configs, it's just going to say, hey, I'm going to use the same analyses for each one. If you did have different configs that required different analyses, so for example, you wanted to use the VLM for one set of analyses, but really wanted to use CFD data for the other, that would be something you wouldn't do a for loop here. You would specify this configuration, I want to use CFD, and this one I want to use the vortex lattice. For this case, we're have one config. This for loop is just going to go through once, and we're going to run these base analyses. Let's go through these fairly quickly. So def the base analyses, and this is another case of things that I usually just copy because the top level stuff really doesn't change much. And I've thought about ways in changing this such that you didn't have to specify them, but for actually good reasons, I have to leave them in there. And I'll go maybe outside the scope of this tutorial, but first I have to set up the analyses here. So this is what this says. Hey, this is basically a container of analyses. And this is what's going to be in there. And so each set of analyses for, I know I'm using the term and it's overloaded analyses, but for any given set of missions, you need an array of analyses that you're going to execute. What this is doing is setting up each one for that mission. So this is the analyses. This is basically a set of analyses. The first one we use is the sizing. There is no way around this sizing one. It's just the default one. It's not necessary to really play with this. We've never need to. But the next one is weights. So each vehicle will have different weights methods. We will not execute this to do a weight buildup, but you could. This is actually set up in anticipation of doing that. And the reason why we're not doing that is because we actually already know the weight of the vehicle because it's on TRI's website, but you could execute this and it would give you the structural weight of the vehicle. The next one is the AeroDes model for aerodynamics. Now there's a paper on this. I'm not going to go through the theory on this, but there's a NASA paper that specifies this is a post-stall model. So this is kind of a necessary feature for any vehicle that's going to transition through stall. If you try to use, like, for example, vortex lattice, it will obviously not be a stalled vehicle because it does not have viscous effects or anything like that. So, the lift will just be linear. You won't actually see the change to the drag regime. So this is a simple model that basically takes the airfoils, makes some assumptions. So we had specified, if you recall, just a symmetric airfoil with a 12% thick. So it's gonna assume an ACA double of 12, and it will build up the drag polars to make it actually transition through. So this is pretty simple, just specifying that and adding it in. Now this next line, and this is another one that I can't really change, and I wish I could default this, but what this is doing, and it seems really obvious why this line just seems kind of useless, but what this is saying is, hey, I set up an energy network. I want you to call that when you need to calculate the energy of the vehicle. And each of those components will then be run with a network, and it will calculate the energy in the batteries, how much is going to the propellers, how much the motors are running, and it'll connect everything through. So this link is actually necessary for energy calculation, because it's giving the mission some knowledge as to what am I actually need to query to figure out where the the power is coming from, the power and energy. The next is planet. The planet, you could change this to be Mars if you wanted to. The default planet is Earth, because we mostly do Earth things. And similarly, the standard atmosphere. So that also is another one that I always just copy through, because I don't have really a good reason to change from the US standard atmosphere. You could if you wanted to, if you happen to know of a different atmosphere here. All right, so the fancy ones are the mission setup. This is actually where I was planning on spending a lot of time, but this went a little bit slower than I anticipated. So this mission is a fully transitioned mission. So it's going to have a hover climb. So it's going to climb vertically. It's going to stay a stationary hover. Then it's going to transition from vertical into the cruise position, cruise for a bit, and then transition back, hover, and then descend. So this is actually quite a complex mission compared to a lot of other things we do in SWAV. And so this, because I have an interest of time, I'm going to have to copy and paste this fast, but I do want to talk through how and why some of the things are in there, and for good reason. So the first thing we're going to do is we're going to set up sequential segments. So that's just going to say, hey, I'm going to have each segment of the mission calculated independently, one at a time. So I'm going to copy this. I'm going to say, hey, I'm going to use the standard atmosphere. A lot of people just use the analyses. You can actually, you've already specified it. So this is kind of specifying it twice, but that's fine. And then the planet. So again, this is a little bit over specified because we already specified it again. And now the segments, this is just like a placeholder for later. It's used kind of everywhere to shorten up names. One thing I do put on every thing here is a base segment. And what this does is allows me to not have to say the same things over and over again. So because this is an electric vehicle, I need to initialize the battery. And so that sets up the conditions required for the battery. So to keep track of the voltage, the resistances, the temperatures, all sorts of parameters of the battery. This line does that. And I specify it once in the base segment, and the base segment gets passed to all the other segments in the mission. I'm also going to skip all the planet positions, so I don't need to calculate. I don't really care what the latitude and longitude of this drone is and see how that's changing. And I'm also going to only do 3 control points at each segment. And the reason for that is there's a lot of segments in this mission. Before I move on, does this make sense where I'm going? I'm setting up some pre-processing of the mission, and I'm going to run a set of segments, and we're going to specify what each segment does. Okay, I'll take silence as a good thing. And if folks have to jump off the call, no problem. I'll just keep going until I get to the end. Okay, so the climb, the first one I said is going to be a hover. So it's going to be a constant speed, constant rate. Now you could do a hover climb here. That's the other option. Both are totally fine. I wish I had done the other one. I should have done one of one and one of the other. So we're going to do a climb hover. What's different here is that I wish I had done the other one actually. Okay, so this is going to start off with the battery at max energy. So charge the battery to start. The altitude is going to be at 0, and we're going to climb up to 100 meters, so about 300 feet. We're going to climb at 3 meters a second. So because we're climbing vertically, the climb rate and the airspeed are the same. Again, we could use a hover mission and just climb at 3. Oh, I do remember why this is here. This does calculate the drag. So there's 2 ways to do hover. One is as a multi-copter, that's the hover function. The climb does this as an airplane. So there is a nuance there. So this is going to calculate the aerodynamics. The climb calculates aerodynamics. Hover does not calculate aerodynamics. The next one is a hover segment, does not calculate aerodynamics. So it's a little bit faster, but this does actually calculate the drag and does incorporate that in the climb. So we're going to copy this through. Actually, there's one other thing I would like to discuss before I copy that over. So this has battery propellers add unknowns and residuals to segment. This is done to change the mission profile. So each type of network has a set of convergence, unknowns, and residuals that are necessary to do the numerics. And this just tells the segment, hey, I need to do this extra numerical computation. Add these to your solver. So that's what this line does. It's a linking there, and this is an initial guess. The initial guess is optional for the power coefficient of the propellers. Let's add that in now. All right. The next one is hover. Again, I talked about the difference between using a climb segment and a hover segment. A hover segment does not calculate the aerodynamics because this is a hover segment, a pure hover, stationary hover, no wind. I'm not going to calculate the aerodynamics. It's just going to do a stationary hover, and we're going to skip that. We're going to hover for 60 seconds, and there's an inertial rotation here. So this is saying, hey, I'm going to take the vehicle and be at 90 degrees. This is something that's specific to a tail sitter. And if you're using, for example, a multi-copter, you wouldn't need to specify that. Your propellers would just be rotated initially into the vertical direction. But because it's a tail sitter, I need to specify that it's actually rotated. Next to transitions. The transitions, one of the harder segments to actually get right. And a lot of this comes down to what your guesses are. As far as accelerations, initial airspeeds, final airspeeds, that tends to fall in there, as well as this initial guess for initial power coefficient, because the vehicle is going to be transitioning through, and there's going to be a wide change in propeller power as you go through. So that getting close on the solver is really useful here. We're going to assume a constant acceleration, constant altitude. So what it's going to say is, hey, the vehicle's here, and it's just going to start moving at a constant acceleration from 0 to 15 meters per second. So there should be a 10-second transition. Now, that's not the only type of transition that SWAV can do for a tail sitter. You could also do a constant pitch rate. So the vehicle starts from here and pitches at a constant rate. There are other ways to transition. We've done optimized transitions, but we found like it really doesn't change too much as far as power usage, and doesn't really change a lot in the conceptual level or add a lot of value. It just ends up being just a lot longer to converge the mission. So we just use for a tail sitter a constant acceleration, constant altitude. So I'm going to copy.
Is this is this calculating the normal forces on the rotors that come from the incidence of the rotor versus the inflow?
Yes. Yeah. So that'll be calculated, and it'll know how much is coming from one direction or the other. That's really the hard part here, is because the blade element process ends up being kind of finicky, because you have some flow that's like directly into the rotor, and then some in the plane of the rotor. So yeah. That ends up being the tricky part there. And that's why we just do numerically something that's like a simple transition. If you try to optimize, the optimizer tends to try something that's kind of crazy, and you get things that just don't want to converge as nicely. But it's numerically all doable, physically all doable. But
and for this case, the aircraft is also trimmed, so those things are or that's kind of ignored.
Yeah, so the vehicle is trimmed as forces. It's not trimmed. We didn't do any control surfaces, if you noticed. This aero model, because it's a post-stall aero model, is not that great to incorporate control surfaces or anything like that. So it's only trimmed in force, but it's not trimmed in moment. Okay. Yeah. Right. So you would need to add another level of fidelity onto this to get the control surface deflections. The cruise is actually very straightforward. So we're going to cruise for 3 kilometers, 15 meters per second. We're going to copy this over. This is very similar to other SWAV tutorials, if you've seen this before. And then we're going to do actually everything backwards. We're going to do a constant acceleration, constant altitude, transition to hover. So one thing to note is that the vehicles usually don't like to slow down in transition. Drag ends up being something that's hard to come by. If you've actually flown this vehicle, the best way to transition it is actually to flip it around backwards, because it then you can use the rotors to slow you down. Otherwise, the airplane's actually really clean. If you do this slow transition, it'll just keep going forever because it's so clean aerodynamically. So this has to be a slow transition back to hover. So that's why it's minus half a meter per second back. And then back 15 to 0, same altitude, and the same initial power coefficients. So that's that. The hover, so this is a stationary hover, no aerodynamics, again, 60 seconds. We'll copy this back here. And then finally, there's going to be descent hover. Again, we have to rotate the vehicle back to that hover position, and then we're going to, oh, this is a normal hover segment. So this is not a climb segment. So this has no aerodynamics. I think the post-stall model did, when I ran this, did some crazy things at this, but we could try it later and see what happens if we did a descent segment. But yeah, this is just going to do just a force balance between the rotors and the weight of the vehicle and have it just descend nicely down to the ground. All right, and then let's return the mission. And for folks watching at home, this will all be on SWAB's website and available to everyone. So this is if you had a set of missions. Again, I'm leaving this in here as a placeholder if in the future you were going to do an array of missions. So maybe you have like different configs with different payloads and you want to run all the different payload combinations. And for example, a lot of times you do maybe a sprint mission or maybe like a loiter mission and you want to change those out. So that's where this comes in. But in this case, there's only one mission. It's just the base mission, and we're going to return that one. Finally, we're going to do the plots. These are just a whole array of plots. This is another thing I copy and paste all the time because I don't really think too much about plots. I just kind of plot them out there. Now, SWAB keeps a lot of data. This is not everything that SWAB has available. If there's another quantity of interest, you could create a new plotting routine and add it pretty quickly. But for this, we're going to do flight conditions, aerodynamics, velocities, the battery pack, propellers, and motors and propeller conditions. So some of these are going to be redundant for sure, because propellers and propeller efficiencies might have two things of the same, and then plot this power loading. Those are kind of things I just copied from elsewhere. Let's see if this runs. If not, we'll run the other